गुड इवनिंग टू वन एंड ऑल। आप सभी को नमस्कार। ऑन द बिहाफ ऑफ डिपार्टमेंट ऑफ मैकेनिकल इंजीनियरिंग, KIPM College of Engineering and Technology, I extend a warm and cordial welcome to all the participants, distinguished speakers, and esteemed guests as we commence the third day of our ATAL Academy sponsored faculty development program on the title Towards Sustainability, the Role of Advanced Materials in the Next Generation Engineering. The overwhelming participation and enthusiasm we witnessed on the previous day have truly set a positive tone for this program. Yesterday's session were highly insightful, enriching our understanding of sustainable technologies and innovative research approaches. Today, we continue this journey of learning and exploration with renewed energy and curiosity. We are privileged to have eminent resource persons who will share their expertise on recent developments in sustainable materials and energy systems, helping us to bridge the gap between research and real-world applications. I once again welcome everyone to this day of intellectual engagement and collaboration. Let us make the most of these sessions and continue fostering the spirit of academic excellence and innovation. So thank you and welcome to day third of our faculty development program. Now, before proceeding for the fifth session, I would like to take a little time to share a brief introduction of our speaker for this session. It is indeed a great pleasure to introduce our distinguished speaker for the session 5 of this faculty development program, Professor Ajay Kumar Yadav sir, who is Associate Professor in Department of Mechanical Engineering at Indian Institute of Technology, Patna. It is my honor to introduce to you Professor Dr. Ajay Kumar Yadav sir, an esteemed academician and researcher in the field of mechanical engineering. Professor Yadav currently serves as an associate professor in the Department of Mechanical Engineering at Indian Institute of Technology, Patna. Professor Yadav's academic journey commenced with a diploma in mechanical engineering from Government Polytechnic Institute, Dumka, followed by a BSc in Marine Technology from Cochin University of Science and Technology, under a Memorandum of Understanding with Indian Navy. He furthered his education with an M.Tech and PhD in Thermal Sciences and Engineering from IIT Kharagpur, completing his doctoral studies. Before his tenure at IIT Patna, Professor Yadav contributed significantly as an assistant professor in the Department of Mechanical Engineering at National Institute of Technology, Karnataka, Surathkal, from 2009 to 2022. His teaching interests encompass thermodynamics, applied thermodynamics, refrigeration and air conditioning, and heat transfer laboratory courses. Professor Yadav's research interests are diverse and impactful, focusing on areas such as supercritical fluids, heat transfer, computational fluid dynamics, bioheat transfer, solar energy, internal combustion engines, and refrigeration and air conditioning systems. He has authored over 100 research articles in peer-reviewed journals and conferences and has supervised 8 PhD and 22 M.Tech students. Additionally, he has secured 6 sponsored research projects from esteemed funding agencies, including the Department of Science and Technology, Science and Engineering Research Board, and Vision Group of Science and Technology. Professor Yadav's dedication to advancing knowledge and fostering innovation in mechanical engineering is commendable. We are privileged to have him with us today to share his insights and expertise. Please join me in welcoming Professor Ajay Kumar Yadav sir, and now I would like to hand over the platform to you, sir, so that we can begin with you with your expertise in the subject matter. Thank you, sir.
Thank you very much. And good evening to all of you.
Good evening, sir.
So, shall I share the PPT? Okay, let me.
Yes, sir. Yes.
Just please tell me whether it is visible or not.
Yes, sir. It is visible, sir.
Visible? Okay.
Yes, sir.
So, thank you again. for why this much lengthy introduction? I thought it is not required this much lengthy.
No, sir. It is my
Lines
privilege to
sufficient.
introduce you, sir.
Okay. So good evening to all participants here.
Good evening, sir.
So we'll start this session, and maybe this is a little bit specific. Advanced material here. Advanced material in this actually CO2 is natural thing, but we are using it higher pressure and temperature, means supercritical stage. So supercritical. This is a supercritical fluid, and means we are making it supercritical and using it. Okay. Otherwise, CO2 is available, naturally available, and this way CO2, you can say if you are releasing CO2, if you are in industry, then it will create global warming. But we are using that released CO2 which is there in the atmosphere. So other way we can reducing the carbon footprint, you can say. So today's talk will be on the supercritical CO2 in solar thermal collector, as well as a little bit few slides I have put on electronic cooling also. So supercritical CO2 we will use in electronic cooling, and solar thermal collectors in that will be the major part. So okay, this is not full slide, I think. Okay, I'm making it full slide. So my talk will cover in this way the motivation, introduction of CO2 system, and suitability of CO2, then solar collectors and different types of solar collectors, and solar thermal power generation system, and disadvantage of water-based solar thermal power plants, supercritical CO2-based gas turbine plants, challenges associated with that. Then summary, this will be the one part. And second part, CO2 in a natural circulation solar thermal collector. Like normal water heater we use. So that type of thing. In that, some results and discussion will be there. And conclusion. Then the last part is SCO2 in electronic chip cooling. So these things I'm going to cover. Now maybe it will take 1 hour, few minutes. So why this CO2, supercritical carbon dioxide? Slide is not moving. Oh, yeah. So motivation behind this is first thing is eco-friendly power generation system using solar energy. So CO2 we are using, one thing always we should keep it in mind, we are not generating CO2 here. So another one thing is solar energy is the green energy, and CO2 also we are using what is available in the nature. A smaller footprint due to high energy density of CO2 system. If you use this, you'll get high energy. Mean to say this is very compact system. Lesser construction material because it is compact, and higher overall efficiency you'll get here. The reason why I'm putting you here this higher overall efficiency, if you what we have done little bit analysis here, as supercritical CO2 power plant gives around 45% to 50% efficiency, and concentrated solar plate. This is concentrated solar plate. If you use CO2, this will give around 60%. So if you multiply this thing, overall efficiency will get 27%. Whereas if photovoltaic cell, if you are using, that efficiency is around 18%. So maybe little bit higher if you use the latest technology, but in this range only, 18 to maximum 20%, 15 to 20. Even getting this also is not easy. Other part now. So supercritical fluid, how you will achieve. The thing is, any fluid if you use in supercritical stage, you will get this type of advantage. Higher heat transfer coefficient, because in near to supercritical condition, the properties are very good for the heat transfer. But which are the fluid available in that range? So if you use water for supercritical temperature, it is 374 degrees Celsius and 221 bar. Water you cannot use in supercritical stage for normal heat transfer applications. Normal mean to say that 60, 70 or 80 degrees Celsius if you want water heating or some type of things. So you cannot use water, because to get water in supercritical phase, you need 374 degrees Celsius minimum temperature, and pressure also very high, 221 bar. If you compare with the water, CO2, supercritical CO2, this is average, atmospheric temperature only. You can see the 31.1 degrees Celsius. At atmospheric temperature, you can achieve supercritical phase of the CO2. And pressure, if you compare, 73.7 bar. So the compared to water, it is 1/3 of the water in the case of CO2. So these are the advantages. If you are choosing any supercritical fluid, you will find the best option is supercritical CO2, carbon dioxide. Okay, most suited and higher temperature required here, 374 degrees Celsius, and you are operating suppose a power plant. So you need to go to higher temperature, 374 and above 400 degrees Celsius. 400 degrees Celsius, if you are operating any solar collector, there will be heat losses, because the inside temperature is more, outside atmospheric temperature is going to be constant. So there will be a big gap. Due to that, there will be heat loss. So efficiency will drop. Okay, most suited with CSP. Last one you can see the CO2 is most suited with CSP, supercritical CO2. Nuclear reactor, waste heat recovery systems to utilize low grade energy. Because here 31 is the supercritical temperature. 32 you can say, little bit, 31.1. So you can use this CO2 for, this is most suitable, you can say. Let us see this suitability of CO2 as a working fluid. CO2, the advantage if you see here, supercritical means what? That is not liquid, not gas, like that, in between type. So you will get advantage of low viscosity of gas here, and density is almost not very low, but not say like a liquid, but it is comparable. 500, 600 in that range you will get, 400 to 600 in that range. And viscosity is less, so pumping power requirement will be less here. Viscosity less, so you will easily get the fluid in turbulent flow. So Reynolds number, because rho v d by mu is the denominator, so you can get easily Reynolds number in turbulence zone. So turbulent Reynolds zone if it is, then heat transfer coefficient will get higher. Then high coefficient of thermal expansion, because it is liquid vapor type of things, vapor you can say, so coefficient of thermal expansion will be more. In liquid it will be very less if you compare with water. So if there is a small amount of change in temperature, this fluid will start moving because volume will change. Whereas in the case of water, this won't move. So the heat transfer coefficient will not be, means will be very less in the case of water. Other properties you can see, non-flammable. CO2, you know, we use for extinguisher, fire extinguisher. Non-toxic. It is not at all toxic actually. You may be thinking if you inhale CO2, you will die. It is not like that. Actually, CO2 is not toxic. If you inhale, your oxygen will get replaced with CO2. That is the problem. CO2 is not going to damage you. You will die due to the shortage of oxygen, not due to the CO2. Other thing is ODP, ozone depletion potential is zero. If you compare with the other refrigerants, synthetic refrigerants, if you consider like chlorofluorocarbons, those are having very high ODP, and GWP also very high. Any refrigerant, if you take R134A, that is around 1300-1400 GWP. ODP is 0, R134A, but R22, R12 ODP is there, ozone depletion potential. So here there is nothing, ODP is 0, GWP is 1, because this is the GWP we compare with the CO2. So CO2, how much it can damage to the atmosphere, that is equal to 1. And here what I am telling you, we are not generating CO2. We are using just from the atmosphere. Okay. Then critical temperature, pressure already explained. Operating condition near critical point offer certain advantage compared to other working conditions. So for this is true for any fluid. Okay. If any fluid, if you are taking near critical point, if you are operating, you'll get certain advantage. But the fluid option, you don't have much. Only a few options you'll have, and best one is the CO2. What is this actually supercritical phase? Critical point, you know, TS diagram you might have studied. Okay, phase diagram you might have studied. So in a TS diagram, if you see the dome, inside below the dome, that is, you will get two phase. And the critical point, that two phase part becomes 0. Okay, HFG, latent heat of vaporization, becomes 0. And that is the critical point. Above that, temperature and pressure, that will be supercritical zone. Okay. And people are also using in a nuclear power plants application, ultra supercritical also. Okay. So ultra supercritical, if you go with water, it is very difficult. Okay, water, if you go, then pressure, you imagine 221 bar is the critical pressure. 221 bar. If you take just 1.5 times, so around 330, 330 bar you need. And the power plant, what we are operating, some are supercritical boilers came in the market. Okay. So water based, because the water is a best fluid, you can say, in the other way. So the normal NTPC, that type of plant I'm talking. So supercritical boilers also, okay, drumless boiler. Okay. That much pressure you have to operate. Here, if you want to operate, if you replace water-based system with supercritical CO2, you need to operate at very low pressure. 73 bar is the operating, critical point. 1.5 times if you take, it will go around 105. 105 and there 300. So 3 times higher pressure. So safety point of view, this will be safer. Then critical pressure, critical temperature getting also easy here. 2 times is what? 31 into 262. So you can get easily this temperature with the normal solar collector. You can get without concentrated also. So these are the advantages if you use CO2. Few things I have put here, properties, just for comparison. You'll have feel that what is the difference between the CO2 and water. Let us see that here. First one, I have taken the liquid state. CO2 also in liquid, water also in liquid. Okay, both are in liquid at same temperature, but pressure will be different. You know that CO2 in the normal atmospheric pressure will be in a gas form. So here 60 bar CO2 I have taken at some 10 degree Celsius, and water also 10 degrees Celsius, but 1 atmosphere. Both are in liquid phase. If you see this beta value is 101 times higher than water. It means if you are heating water, in the natural convection I'm talking, if you are heating water, this volume change is 100 times. So volume change is 100 times means it will start moving. Okay. So movement here, it will be faster, the beta. Okay. So you will get higher Reynolds number also due to that. Other way, another one we can see the other part also, you can see Cp value of CO2 is less. Water 1.5 times than CO2. Both the lines are same here. Both rows, water by CO2, CO2 by water, both are just 1 by inverse of this another one. So this is, you can say Cp is higher in this case. But Cp is, it is not always true. Cp you can see here 3 times higher than water. CO2 Cp is higher than water in many cases, in many points. Okay. I'll show you. Conductivity is higher, no doubt, of water conductivity is higher. Mu viscosity, you can see, water viscosity is 14 times higher. Density is, okay, not much, comparable, you can say. Okay, 1.1. Prandtl number is this much. If you compare in the supercritical, this is liquid, so subcritical, compare supercritical side if you go. So supercritical, why supercritical is advantageous? Just you can see here. The ratio part, beta, you can see it is much more than liquid stage, and now the supercritical state, you can see the difference 256 times, very high, and Cp also very high, 3 times. Water, so Cp is very important part. If you have higher Cp, your temperature change in temperature, or you can say heat carrying capacity will be more. For 1 degree temperature difference, it will carry 3 times higher. You can see the 3, if the Cp is 3 times higher heat than water. Okay, conductivity is, yeah, one bad thing here is conductivity is less. Mu also, they can see water mu is much higher, 18 times higher. Okay, so, and density is twice, water density is twice than this. So this is the main advantage. Due to that, you will get the advantage in heat transfer rate, heat transfer coefficient, those things will get. Similar way, another one, CO2 90 watt, 323 Kelvin. There are different, if you go to slightly higher temperature, what would be that? Still we are getting advantage here. Here I have put some heat transfer loops. There are, forced circulation and natural circulation. Natural circulation, you don't need any moving component. Automatically it will circulate due to buoyancy driven forces. Okay. So if you are heating, density will change, and that due to that density, it will start moving, buoyancy effect will come and circulation will set up. But for circulation loop, you need pump. If you are using pump, you can circulate at higher velocity, higher Reynolds number, you will get higher heat transfer coefficient. So these are the things. So the thing is, if you use normal water collector, you might have seen water heater, solar water heater. There is no pump in that. If you use pump, then again electricity required in that. Again, you use a small PV cell you put there, then it will circulate. So that is not required. So natural circulation type is preferred here. There are many places where we use natural circulation. In a power plant, in the gas, in a boiler part, that furnace, boiler, complete part, if you see there, in a furnace, there is a heat generation, heat supplying heat by burning fuel, and these tubes gets heated. Inside that, there is a water or CO2, you can say. Water, if you consider here. So this will get heated and it will come like this. So there is no pump here for recirculation inside the boiler. Okay. Furnace is the part of boiler, you can say, inside. There is a boiler drum, and there will be tubes. So there is no pump here. If you put pump, the huge amount of power you need to supply, to recirculate it. So you cannot use here, because the whatever you are getting energy, you may need to supply good amount of that to circulate the water. Okay, so we use natural circulation only. So here, if you do the study, water and CO2, you will get CO2 will give advantage. It will be advantageous to use CO2. So wherever the NCL type, natural circulation system is there, then water CO2 will be advantageous, because beta value is very high in the case of CO2. Application of NCLs, you can say here, thermal power plants, solar heaters, refrigeration, air conditioning, geothermal application, new generation nuclear reactors, electronic cooling system. Okay. So these are the just introduction. Now we'll start our work. This work, this is actually experimental part, and this photograph, this is a schematic of that. This was done by my PhD student, Tippeswamy. This is natural circulation loop. The simplified version here we have taken, and we wanted to compare water and CO2 performance. Maintaining the same temperature inlet, mean to say hot heat exchanger here, you are heating here, here it is cold heat exchanger, you are removing heat. So there is this is just one tube bent in a rectangular form or a square form, you can say this tube. And we have filled CO2 inside that. And we started heating from here and cooling from here. And we want to see what is the heat transfer rate. Very simple. This is supercritical CO2. Then we will remove this CO2 and we'll put water only. And we will see what is the circulation rate. Not circulation mean to say heat transfer rate. Very simple, nothing change. Temperature we are keeping same. Inside fluid only we are changing. Cold heat exchanger, hot heat exchanger, same temperature we are keeping like this. Okay. And changing the fluid only and we will see the performance. And this was totally experimental study. Doing experimental study in a supercritical fluid is very risky also. Very few papers you will find. So here we have done even only supercritical CO2. If it is there, then easy to do, not very risky. But if your fluid is changing from, if you are using liquid two-phase CO2, because it is sub-zero temperature or below your atmospheric temperature. So below atmospheric temperature, or sometimes suppose power goes off, power is not there and circulation is stopped, then there will be blast here. Okay, explosion maybe in this because the liquid to vapor pressure will rise. It will automatically due to heating from the atmosphere. So this way it is very risky. These are cooling and heating to bath we have put here. Okay, thermostatic bath for the cold heat exchanger and hot heat exchanger. And we have put temperature, we have measured the temperature or the differential pressure transducer we have put to find the pressure drop. This result, these are the interesting result. It was published in scientific report. Here if you see what we have changed, just fluid we have changed, same temperature we have kept. So if you see this, the reason here, you can see here water performance is very low. Here you can see the bottom one. How much heat transfer rate, you can see it is around 100 watt. But other cases you can see 500, 600 is going. So this much difference is there, heat transfer rate. We are not supplying heat flux here. We are supplying heat temperature we are keeping fixed. Okay, water we have used in heat exchangers, cold and hot heat exchangers, and that water inlet temperatures in heat exchanger keeping same. Not the internal fluid. Loop fluid, we are not doing anything. Loop fluid we have just filled and closed it. And the outside heat exchanger temperature we have controlled. Kept the same for water and CO2 cases. We can see here 400% improvement we got in heat transfer rate compared to water. Another case, if you take, this is subcritical vapor, subcritical liquid. This is the, I'm not talking about the supercritical, this is the subcritical, lower pressure. Lower pressure also we are getting, these all you can see the experimental results. Here you can see 500% improvement. So same temperature range, TH minus TC in x-axis you can see. Okay, hot heat exchanger and cold heat exchanger temperature difference. If you keep the same, suppose 18 degree, if you compare 18 degree, here is the water and these things are the CO2 at different pressures we compared. So these are the results you can see. Now we will see to the supercritical stage what happens. If you see the supercritical and two-phase, two things are there. Supercritical stage, if you see, you can see this performance here. This is 100 watt around, this is not changing. Okay, because we have changed the temperature actually. Here, temperature we have changed, supercritical to reach supercritical. Temperature and pressure we have changed for CO2. Temperature will be same for water also, but temperature, pressure if you change for water also, suppose you want 90 bar, you make it water also, that won't change anything. Because that is incompressible fluid, liquid water. So even if you increase 90 bar pressure, we have done that also, that there won't be any effect on the performance, because property is not changing. Density will not change when you take it 90 bar or 1 bar water. Incompressible. So that is the thing. The pressure does not matter, you can say, for the water, but CO2 it matters. So you can see that here we are getting 800 times improvement. It means what? 8 times smaller size you can achieve the same performance. Means it will become very compact, very small size of CO2 if you are using supercritical CO2. 8 times you are getting. Now you go to the two-phase. Two-phase requirement based on the temperature also here. Two-phase, getting two-phase of CO2, you need to go to almost in 31 is one thing, 31 degrees Celsius. If you go to, we have done variety of experiments, even we have gone to the below 0 degrees Celsius also, -10, -15 in that range. So -15, -20, when we went to that level, in that we cannot use water. You know, the water will freeze at 0 degrees Celsius. So we have used brine solution we have used. So here we can get 900% improvement in transportation. Now we'll go to the solar collectors. What are the different types of solar thermal collectors I'm talking here also. So these type of collectors you might have seen. This is we created earlier. I was at IIT, so they are supercritical CO2 based flat plate collector. We did experiment also on this, and this is from the website we've taken. Evacuated tube. This is the flat plate collectors normal. This is evacuated tube. And this is parabolic trough collector. If you want higher temperature, then parabolic trough collector. Then this type is very high temperature. You need 800, 900 degrees Celsius. You can go with this. And using this, some places you can say the thermal power plants were operated or are getting operated also, or being operated. So these type also people have used concentrated. These are concentrated type. But this maximum temperature, how much we can achieve? Flat type, if you use 80 degrees Celsius. Evacuated tube, 180. This much range you can go. Parabolic, 400, and this type, 900. See, the higher temperature getting, you may need to run power plant. You may need higher temperature. But the thing is, as you go higher and higher, your efficiency will drop due to the heat loss to the surrounding. So if you see this paper, it's not my paper, it is published in Applied Energy, mass. This paper, if you see, as you increase the average temperature above ambient, okay, 200 degrees Celsius, 200, 300, 400. If you go this type, then it will be 800, okay, 900, that range. It will go much lower efficiency. So the efficiency, if you see collector efficiency here, you can see initial at this temperature around 80 degrees Celsius, you can say. This is actually above ambient, okay. Efficiency around, you are getting around 72, around in this range. As you go down, here you are getting in this range around 56 or something, okay. So this much drop in efficiency you are seeing here as you increase the collector temperature. So what options we have? So if you use water, as I told, you need to go to the higher temperature to make it vapor. Then you use in power plant, steam power plant. At least 1 atmospheric pressure nobody uses. You will go for slightly 5 bar, 10 bar pressure. So you may need around 150 to 100 degrees Celsius. This is the normal, I'm telling you. But you will get very less efficiency. As your temperature increase the temperature, you will get higher efficiency. Very, very simple. And vapor is must get to operate this thermal power plant, steam power plant. Here in the CO2 case, supercritical CO2 case, you may need, you don't need to that change that because the 31 degrees Celsius is the critical point. Above that is in vapor form. So here you need low temperature. You do not require that very high temperature. But one thing is always there. One thing will be there. To get higher and higher efficiency, temperatures matters. Okay, that is one thing. Supercritical CO2 based gas turbine power plant with concentrated solar collector. For the gas turbine, just I have put some slides. So high temperature requirement to generate steam. This I already talked. Efficiency of solar collector will reduce at higher temperature, right? Low efficiency, very difficult to achieve. Supercritical stage to obtain better efficiency. If you are operating in supercritical stage. 221 bar. This is this already talked. Large size due to high specific volume of steam at LP turbine. This is important one. Size is very large. If you talk about the steam power plant, LP turbine, low pressure turbine side pressure is condenser pressure. Condenser pressure is how much? 8 kilopascal around. 8 to 10 kilopascal in that range. 8 kilopascal. That is very low pressure. 103 around 1 bar. If you say 100 kilopascal is means 1 atmospheric. 1 bar around if you say 100, and this is 8 kilopascal. This much difference, 12 times. So volume will increase also. So you need very large size of LP compressor. Sorry, LP turbine, low pressure turbine. So that if it is size is large, operating at higher speed, balancing all things matters. So as it is, if it is compact, very small size, it is very easy to operate. So here in the case of CO2, because the pressure is higher, we need not to go to that 8 kilopascal. Pressure is higher. How much pressure? It will be around 30 or 60 bar in that low pressure side also, 70 bar. Even higher also, 90 bar also you can operate. So at 90 bar, it will operate like liquid. And compressor power, what you are going to supply, that will reduce. Let us see this. This is one compressor and turbine setup, and here it is solar heater, solar collector, this side, parabolic type. It's coming like that. So main advantage if you are using air, and here we can compare with air, multi-gas turbine it is, not the steam turbine. If you are using air at same pressure you use, what's the CO2 we are using? Okay. So what the advantage actually we are going to get here is, the main what happens here, in turbine you are getting work, and compressor you are supplying work. The difference between these two you are going to get in generator. Okay, and that will give you efficiency. Now the thing is, if compressor power if we can reduce, how will reduce? So if the compressor inlet, the compressor handling fluid behaves like liquid, if it is, then power requirement, minus VDP. VDP minus VDP is the compressor power. So V, if it is small, V is specific volume. Okay. So V, if it is small, then DP will be same. Then you need to supply less amount of power in compression. So here in the case of CO2, will operate, it operates in such a way that supercritical zone just below the near to supercritical, critical point you can say. Supercritical, there are above that supercritical, but near to critical zone if you operate, and we have like liquid. It is gas, but density is high. You will get compressor power will be less, turbine will be as it is, minus if you do, you will get higher work and higher, finally higher efficiency. This is the advantage here. I have just done the thermodynamic analysis, one small analysis I have done, using the air at same pressure and temperature, and CO2 at same pressure and temperature. Just to have put in the solar collector and gas turbine analysis you have done, thermodynamic analysis. What we got, the analysis, you can see this plot. Thermal efficiency, if you see in the case of CO2, it is pressure of suction pressure of CO2 is 90 bar here. Okay, and discharge pressure is varying here. You can see the in x-axis is the discharge pressure. A small pump type of things or compressor, you can say, small pressure ratio. 90 bar to 120, what is there? Nothing. 1.2 times, okay, you can say 5 times. If you use 140 bar, you can see optimum you are getting higher efficiency. 90 bar suction and 140 bar discharge. So 1.5 times only pressure ratio, not very high. With that only we are getting here, you can see the efficiency around 45% here. And in this case of air, we are getting only 31% around. This much jump is there. See, the same fluid here, same condition, operating condition, same. Air we are using same pressure and temperature. CO2 we are using same pressure and temperature. The reason here is CO2 is in supercritical stage and near to critical point if you are operating. If you are operating very far away from the critical point, also you will not get advantage. Near to critical point, you will get advantage. Okay, so this is the disadvantage we are getting here in this case. And we have, you can see 45 and 32%, this much efficiency jump we are getting. Okay, so we have done little bit safety analysis also to heat exchanger design, whether it will be very bulky. We are getting higher efficiency, but without CFD, that was thermodynamic analysis. And this will give you the size of the heat exchanger, thermal collectors, those things. This also matters. We have done this and pressure drop, those things also we have found comparable here also. We have taken the at velocity, constant velocity for both, means velocity we have compared with the velocity. Actually, we should compare with the mass flow rate. But if you say the same velocity, if you are keeping, mainly the power you will get in terms of per kg. Okay, now. So what is the mass flow rate of CO2 or air? Based on that you will get. So you will see this, if the same, even if you keep the same, because the density difference, just I'm comparing the density of CO2. In one case, you can see here in the third line, density of CO2 is 164, whereas air density is 90. Okay, this much difference is there. Another one, density, if you go to the suction side of the compressor, CO2 density is 667 and air density is 102. Same pressure and temperature, 90 bar. So 6 times higher mass flow rate you will get. So this is a big achievement, you can say. For 6 times higher with the almost same pressure drop, you are getting 6 times higher mass flow rate. So here the size of the heat exchanger also will reduce. That I meant to say here. This was a CO2 power plant at Sandia National Laboratory, US. They developed and they are claiming the efficiency is around higher than 50%. Okay, I got just thermodynamic analysis, it was around 45%. Here 50% they are claiming. Just I put from the website. So challenges, what are the challenges in developing the supercritical CO2 plant? So challenges are there because normal gas turbine, if you talk, that pressure ratio is around 8. So pressure ratio around 8, 10 in that range. Okay. Here pressure ratio is also less, 90 to 140, as I told, CO2 case. 90 to 140, the pressure ratio is 2, you can say. But the pressure, the total pressure, you can say, the suction and discharge. In an air gas turbine case, suction pressure is 1 atmospheric. Discharge pressure is 8 bar, 8 atmospheric pressure. Only 1 and 8 bar, very low pressure. Here, 90 bar and 140 bar. This much their difference. 90 bar, it should hold. Compressor, turbine, whatever the parts we are making, that should hold that much, should be capable of holding that much pressure. This is important part here. There is a big challenge. Other thing is seal design. 1 bar, there is no that much leakage of CO2 or air at 1 bar. The pressure is very low, 8 bar, 5 bar. Here it is 140 bar. So seal design matters. But we have the technology. It is not we don't have technology. We are using steam power plant, steam turbine at that high pressure. Steam turbine, you know that steam turbine operates at a very high pressure. Is there are supercritical boilers also, so it will be might be operating 250 bar. We want here 150 bar only. So technology is there. So if you do the some BHEL or something, BHEL or some GE, you can be developed this type of things, and some people are also started developing this. So this is the sealing part is the important issue. Okay, and there is fluctuation in properties in the case of CO2. Okay, for the small 2-3 degree temperature difference, there will be huge jump in properties. That also we have to take care. Okay, suitability of materials of the CO2, if you are using CO2, whether it is how much corrosive or not, that you have to see. These are the application. So gas turbine industry, geothermal application, people are also using this. Nuclear part CO2, people many in the park also BRC people are doing study on supercritical CO2. In defense it is there, and this thermal power plants, solar thermal plants, nuclear plants. So conclusion is like this: new emerging technologies based on SCO2 combined with CSP as heating source is a promising technology for sustainable development. CSP means concentrated solar plate. Okay. This system is eco-friendly and having very low running and operating cost, because this is based on the solar. So running cost, operating cost will be low, but initial cost will be more, right? Now we are going to start the another part of this. Working fluid in solar thermal collector. Okay. So water heater bulb, that part we're going to cover now. So application in solar water heater. What is the reason why we have chosen this? Okay, solar water heating system is inefficient during winter due to the chances of water freezing and higher viscosity due to low temperatures. So if you are using simple flat plate collector, then this issue will be there in that. Inefficient, chances of freezing, also low temperature and higher viscosity due to low temperature. Higher viscosity means it will not start moving, so heat transfer coefficient will be less. Let us. We have done here some CFD study and experimental study. One of my PhD student did this, Madhu Viradar, Dr. Madhu Viradar. So CFD part, I'll show you here. What we have done, just schematic I'm showing you here. This part is solar collector part. One tube we have taken here, considered. And this is heat exchanger part inside this tank where the water is there. Water to be heated here, inside water is there. And this inside the loop, there will be CO2. So advantage here is if you put inside loop water or without loop directly, if you are connecting this to this water, if you are in the morning, in the winter time, getting heated, this will not start moving because due to the low temperature, there will be higher viscosity. It will not move. So you will not get hot water. In the case of CO2, what will happen? A small amount of heat, if it gains, it will start moving to the heat exchanger. So some amount of heat absorbed here, it will go and deliver to the water here in heat exchanger, and it will move back. It will start moving fast because low viscosity. So this type of study we have done, we have considered different types of solar radiation value here and different pressure of CO2 considered, and we did a study and compared with the water. If we are keeping water, certainly water will be in the laminar region, so we'll get less heat transfer coefficient. The temperature will be less in that case. Then here temperature will be less. So these are the things range we have considered: 400, 600, 800, 1000 watt per meter square. This is solar radiation. Velocity of water in heat exchanger. That even if you don't give velocity 0 and tanks directly putting the tank, okay, how much time it takes to get heated to some 50 degrees Celsius or something. That will be type of transient study, but we have done a steady state study here. So some fluid velocity we have put there in heat exchanger, because tube in tube type heat exchanger we have taken in CFD study. So these are the things. And subcritical liquid and vapor, we have used subcritical also, supercritical 80, 90 and 100 bar pressure. 3 pressure supercritical, 3 pressure in subcritical. And temperature, we have considered 2 temperature. One is like winter type of weather. Winter weather means 10 degrees Celsius, 278, 5 degrees Celsius, 278 Kelvin. And another one 305. So these 32 degrees Celsius. So these 2 conditions we have considered in winter and summer case, like that. And collector tilt angle 33 degree. So collector tilt angle also we have done a study, different tilt angle also, but here we are showing, I am showing only one. This study, if you do that, water we are keeping inside, temperature we are keeping same, and comparing it. So here also, as I showed you earlier, that heat transfer rate, but in that case there was heat exchanger temperature was kept same. That hot heat exchanger and cold heat exchanger. Here it is heat flux we are supplying, because solar radiation is there, so heat flux you have to supply. So heat flux, when you are supplying, what is the Reynolds number, what is the Nusselt number, and those things we will find out here. So you can see the same amount of heat flux we are giving here. You can see the Reynolds number is varying in here. It is in varying in 6,000, 7,000. In this, it is 2 digit, 40 to 60 in this range. Similar way, you can see if it is subcritical vapor. This is at 305 Kelvin. First one was 270 winter. This is summer. You can see. You can see the in summer case water performance improved. You can see this. This is becoming 110 around. It was here in 60. It's doubled. And Reynolds number increased in this case. CO2 case also, both cases. So times, if you say times 200 times higher, Reynolds number. In supercritical case, 260 times higher, you can see Reynolds number. This was published in Renewable Energy. Sorry. Okay. So this is the comparison between water and CO2. This is the properties. Earlier also I showed you why this thing happening. The reason is ratio of volumetric coefficient. So this is going around 500 times, but based on the operating temperature. In both the cases, what is the temperature, pressure we noted, and we found the volumetric expansion coefficient. We found in this much range. Okay. So these are the reasons. Here also you can say at 305 Kelvin, this much change is there. And this is also similar way comparison is there. We'll go to the Nusselt number. Nusselt number, if you see, 13 times higher Nusselt number we are getting. So Nusselt number depends on the Prandtl and Reynolds number. So you have seen the Reynolds number is increasing very high, but Prandtl number is not in that way. So that's the reason we are getting 13 times here only. Otherwise, Reynolds number was in the range of 200 times. So 13 times, because the conductivity of water is good. That also matters here. 19 times higher Nusselt number. Supercritical CO2 48 times. Average, we are saying supercritical CO2 is very better compared to the subcritical. Energy efficiency, if you consider. So final thing is how much energy efficient system you are getting. Main thing is that. So energy efficient system, we are not getting much higher. So you are getting around at 50 bar liquid side, you are getting 5.6%. For vapor, 8.5% change, and supercritical you'll get around 12. Just let me see. Supercritical 12.2%. Higher efficiency, thermal efficiency of solar collector. So 12% higher you are getting compared to water. It's not less. Okay. So this is the thing. Yeah, the summary of this, you can see here. Two cases. First case is winter, 278 Kelvin. Second case, 305 Kelvin. Summer, you can say. And these two are summer case. One case supercritical we are comparing, another subcritical only, and this one subcritical liquid. But winter case. Supercritical you cannot use in winter case because the temperature requirement is higher there to achieve supercritical fluid. So in this, if you compare, you can see this Reynolds number, how many times increasing, Nusselt number ratio is given, CO2 by water, mass flow rate, CO2 by water, this much times increasing. Then efficiency, this is first law efficiency, eta CO2, thermal efficiency, going 1.12 times, means 12% higher than water. And this is exergetic efficiency actually. Exergetic efficiency is higher, 1.5, 2.4. The exergy analysis also we have done. I have not shown you here that result. So the CO2 based system shows excellent performance in naturally circulated solar thermal collector, which will be useful in designing compact solar water heating system for winter as well as summer. Now, few slides I have put here. Much time is there. So electronic chip cooling using supercritical CO2 in microchannels. So this is very good area of research because as the electronic system is divided, increasing and becoming compact, we have to remove heat from high amount of heat flux. We have to remove from a small size of the chip. So that is becoming challenge from our side, thermal engineers. For thermal engineers, we have to take care of this heating part. And similar way, this maybe can be used in battery cooling also. Okay, so in that thermal runaway, we have to shape that there is an issue in battery cooling, electronic battery, electric vehicle battery I'm talking. So, but this part heat generation is more, electronic chip. Battery cooling heat flux is not that much. Here it is very high. If you are able to deal this, then that will be easier. So we have used here supercritical CO2 in microchannels. Okay, let us do this. What is this microchannels? You know, very macron size. Microchannel mean to say around. If you use, generally there are different concepts. Even the 10 micron to 500 micron. Some cases 200 micron. People say 200 micron is the microchannel, but in this range you can understand. So around 200, 300 microchannels, that diameter or hydraulic diameter should be in that range. Here what happens if you are using microchannels, your surface area to volume ratio increases. So heat transfer depends on the area. If area is more, heat transfer will be more. Okay, HA delta T. So area we are increasing here by putting the small microchannels in that. This is the advantage. Now the thing is, if you use water in that, most of the cases people are using water. If you use water in microchannel, rho V d by mu, okay, d is small, very small. Mu is fixed of water. Rho is velocity, how much you can put in water. So diameter is very small, so it is very difficult to achieve turbulent flow in microchannel. If you want to achieve very unrealistic velocity, you have to put water velocity inside. which will create very high jump in pressure drop, high pressure drop. So that is even not possible, you can say, unrealistic, that velocity. So water, if you want to remove heat in large amount, you need turbulent flow, one thing. And turbulent flow with liquid, with water is very difficult. Here what we can do, we can use supercritical CO2. It has very low viscosity. Viscosity is low. So with that you can get Reynolds number in turbulent phase. Okay, so this is the advantage what I am explaining here. This is a very, so advantage thing you will get here. But there is a disadvantage also. You are using high pressure things. CO2, if you are using here in supercritical, means 90 bar, 80 bar you have to go. Even 75 bar around. In that range you have to operate. But the size is small. Macro channel, this amount of CO2 used in the macro channel will be very small amount. So even if it explodes or something happens, it will explosion energy will be very less, because the amount is very less. And as you use a smaller channel, even the thin size tube can sustain very high pressure. Okay, you know that it stays in a small thin tube or large tube. Even if it is small, then that depends on the diameter. It will the requirement will be, the thickness of the tube will, the requirement will be less. A small tube can take higher pressure. This is the proposed computational model. Proposed means we have done already. Sorry, proposed is not right. So this is the computational model. Okay, microchannel. Different mass flow rate we have considered here. Mass flow rate we have kept same for the case of water as well as in CO2. And we did some analysis here. We have used ANSYS event for this. At a different pressure in water we have used. So just few results I have put here. So the dimension you can see here, 10 mm and 40 mm. 3D analysis we have done, and here channels we have put a small tube for diameter we have considered 0.2. You can see. Okay. This is meshing and grid independence test. Final results I am showing you just recently published in Applied Thermal Engineering. This work was done by my PhD, M.Tech student Sushant, and we have colleague Karim Khan. So all three we have done this study. You can see here the temperature. One result I have put here because it was going to be lengthy presentation. So this part you can see here, THPP matters. THPP means what? How much Nusselt number you are getting, higher Nusselt number compared to the how much pressure drop is there. Both. In some cases what will happen, you increase the velocity, you will get higher heat transfer rate. But if you increase the velocity, you will need to supply more power in that. So pumping power is increasing and you are getting higher Nusselt number. So how to do the trade-off? Somewhere we are getting higher, but we are putting higher pumping power also. So there is an equation. That equation is THPP actually, that parameter you can see. In that Nusselt number is compared with the Nusselt number in the here we can say CO2 case or water case, ratio of Nusselt number divided by ratio of friction factor. This is called THPP. But in this case, because the fluid is different, if fluid is same, that you should use Nusselt number, ratio of Nusselt number divided by ratio of friction factor to the power 1/3. This is the thing. If fluid is different, you should not use that, because the delta P is different here, very large. If large delta P is there in the case of CO2 and water, not comparable, then you should not use that, because the fluid is different, there is a chance of large delta P. So we should use the heat transfer ratio divided by pumping power ratio to the power 1/3. Earlier case, Nusselt number and friction factor. Here, heat transfer by pumping power. So this way we have done, we got 7. if you use, we have done both the calculus. If you use earlier equation, Nusselt number by this friction factor, we were getting this 40 or 50 in that range, 14 THPP. So this 7 or 8 times more compact, you can say, this system is. So this can remove same size of channels. It can remove 7 or 6 times a higher heat transfer rate here. Heat transfer. Okay, so this is the thing. This is the conclusion of this second study. Thanks for your attention. Any question if you have, please ask. This is the IIT Patna campus, admin block and library.
Thank you, sir.
Okay, welcome.
It
Stop
is indeed.
sharing. I should stop, I think.
Yes, sir. Yes.
Stop sharing.
It is indeed my privilege to extend our heartfelt gratitude to you, sir, for delivering such an insightful and thought-providing lecture on the supercritical carbon dioxide for solar thermal collectors. Sir, your talk has provided us with a deeper understanding of the emerging technology, innovative practice, and sustainable trends that are transforming the automotive industry. Your ability to connect the theoretical concept and real-world industrial applications, and you truly enrich our knowledge and inspired us to think critically about the evolving role of advanced materials and sustainability in engineering. Your experience, valuable insight, and practical examples have added great value to this faculty development program. The clarity and relevance of your presentation have undoubtedly motivated all participants to explore new research and adopt innovative teaching and learning approaches in the field. On behalf of Department of Mechanical Engineering, the organizing committee, and all participants of this FDP, we sincerely thank you, sir, for sharing your time, expertise, and wisdom with us. We truly appreciate your contribution and hope to have more opportunity to learn from you in the future. Thank you once again. Thank you, sir. And thank you to the audience for your active participation in the session. We will now take a short break before proceeding to the next session for our faculty development program. The upcoming session will begin shortly and promise to equally informative and engaging. I request all participants to kindly rejoin after a 15-minute. The Google feedback form of the current session will be shared shortly in the group. Thank you. Thank you so much, sir.
Thank you. So there is no question? Or
No, sir.
shall I log out?
Yes, sir.
Okay. Thank you. Thank you very much.
Thank you, sir.